In this video, we're going to look at section 13.3, which is on partial derivatives. Okay, partial derivatives. The skills that you need before you attempt this section, skills needed. Skills needed are 1, you need to remember that when you take the derivative with respect to t of a vector valued function in one variable, that what that means is the derivative with respect to t. Your vector valued function is of the form x of t, y of t, z of t. That the derivative of that vector valued function is just the derivative of each entry of the vector as a Calc 1 problem. So you would then need to compute the derivative of each entry with respect to t. So to do this, you'll have to do 3 Calc 1 problems. Okay. The second thing you're going to need is to remember is the concept of a curve on a surface. Okay, we've done these a lot in class. The curve on the surface, let's call it C of t. The curve on the surface is the form where you pick an x of t and a y of t. And that the z value is not just anything, it is the function of 2 variables that you were given, and then you're plugging in the x of t and y of t value, where your z entry is the function evaluated at x and y. So these are the 2 skills that you're going to need to do partial derivatives. Okay, so let's look at a calculus. Let's look at a Calc 3 problem where I take the function f of x and y and take function x and y to be x squared times y. So here's your function of 2 variables. Okay, and the book goes through a method. We'll call this method number 1. Method number 1. For computing, there's 2 first partial derivatives, partial f with respect to x, and there's another symbol called the partial of f with respect to y. Okay. So you could write partial f with respect to x as partial f with respect to x, or you could write partial f with respect to y as f sub y. Either way, either notation will work. Thing to remember, note that the partial derivatives f sub x and f sub y are most likely, in general, and most likely functions of the variables x and y also. So sometimes you will see the partial derivative of f with respect to x written as x comma y. This piece here indicates that it's a function of x and y. Okay. So what you could then do, method number 1 is to say that the partial derivative of f with respect to x, for example, the book goes through the process of saying that this is the derivative with respect to x of the function f, and it's a function of x, and you hold y constant. Okay, in your book, they use this to be some blue variable, but since I'm not going to write it in blue, I'll just put square brackets around it to mean that y is held constant. Okay, so when you're differentiating it, just treat it like a constant. So in this case, your function will be x squared multiplied by y, where y is a constant, and therefore you need to take the derivative with respect to x of this. And because y is a constant, I can bring the y out in front of the derivative symbol, and you just have derivative with respect to x of x squared. So the answer will be y. The derivative of x squared is 2x. And so your final answer, you can take the square bracket off of the y, and here is your partial of f with respect to x. And notice that it is a function of both x and y. Okay, so this is the shorthand for it, and it's probably better to write this. And I would say this is really shorthand. This one is better because, for example, I could ask you the question, what is f sub x? What is f sub x at the point, say, 1, 1, right? in which case you could write f sub x evaluated at 1, 1, or you could write f sub x evaluated at x is equal to 1 or y is equal to 1, in which case you would put 2, 1 times 1, which is 2. Okay. You could turn around and do the same thing for f sub y. I could say find partial of f with respect to y, or f with respect to y, which by method 1 would be the derivative with respect to y of f, the function f where you hold x constant, and then you let y be the variable for the problem. So we're just reducing this down, calc 3 derivative, which is a partial derivative, and this is just a calc 1 problem. So our function here would be x squared times y, and we're going to take a derivative with respect to y, in which case x squared is a constant because x is a constant, and you need to take the derivative with respect to y of y. So your answer here would be x squared times 1, or just x squared. So the partial derivative of f with respect to y, or the partial derivative of y as a function of x and y, is x squared. This function, x squared, happens to be missing the variable y, so it's not really a function of it, but it could be a function of x and y, like in the previous case of f sub x. And now I could follow that up with, I could say, find f sub y evaluated at 0, 3, in which case you would get 0 squared, which is 0, or I could say f sub y at 1, 1, and that would be 1, or I could say f sub y at 3, negative 2, in which case you would get 9. So all these examples. Okay. It's a different matter to address what these partial derivatives are actually telling us. Here I've just taken some derivatives, some partial derivatives, and I'm getting these numbers. So in general, the computation 1. We have in general, you can ask for the computation of the functions f sub x and f sub y, or you could ask for the computation of f sub x at a particular value, say x naught, y naught, or f sub y at x naught, y naught. And what I mean by that is where x naught and y naught are given. These are some numbers that you're picking. So for example, in this problem, x naught, y naught was 0, 3. So I mean, it's one thing to do these computations. It's another thing then to know in general the computation. There's a computation step. The second thing that you really need to talk about is the meaning of these numbers and the use of these numbers and the interpretation of these numbers. Okay, so let me show you the second method for computing partial derivatives, and then in the second video I will discuss more on the meaning. So in this video we'll just focus on the computation of these partial derivatives. Okay, so method 1 for computing partial derivatives, f sub x is the derivative with respect to x of f of x, and you hold y constant. Okay, f sub y, derivative with respect to y, f, hold x constant, and then let y be your variable. Okay, and in both cases, these would be your partial derivatives, and they will most likely come out to be functions of the two variables. Okay, so what we're talking about here is you had to first be given a function of two variables, an explicit function of two variables. Z is equal to f of x and y. So your function here has only these two variables in it, and for each variable you can compute the partial derivative with respect to that symbol. Okay. So that's method one for computing partials, and you should probably maybe try, for example, now let's say I give you the function f of x and y is x squared y cubed plus cosine of x plus y squared minus sine of x squared y. This would be a good example to test to see whether or not you can compute f sub x and f sub y. All right, we're back. So you should probably have attempted the computation of those derivatives. I will do one of them now. I'll fill this one in. The partial derivative of f with respect to x should be 2x y cubed plus the derivative of cosine of x plus y squared with respect to x. Derivative of cosine is negative. This should be a negative sign, sine of x plus y squared, times the derivative with respect to x is 1, minus the derivative of sine is cosine, x squared y, multiplied by 2xy. So there's your partial derivative with respect to x. And I will leave it for you to try to compute the partial derivative with respect to y. Let me at this moment show you how to check your answer in Mathematica. So here is a Mathematica window. Let me make it a little longer and skinnier here. So here is Mathematica. Again, you had to be given a function f of x and y before you can compute some partial derivatives. So go ahead and make your function f of x and y. Okay, this should be old hat by now. X squared times y cubed plus cosine of x plus y squared minus sine of x squared times y. Make sure you've typed that function right, x squared y cubed, cosine of xy squared minus sine of x squared y. So I feel like I got the function typed right. And now it's a really simple matter to compute the derivative. Let's go to the next line here, and you could say, sorry, enter. Take the derivative, d, of this function f of x with respect to x. And hit shift return, and here is your answer for the partial derivative of f with respect to x. So this is your answer for f sub f sub, oh, why can't I do it? Control, there we go, f sub x. Double equals, I wanted to print to the screen, true. Never mind, I could talk about how to do that. So there is your derivative of f with respect to x. You can see it's 2xy cubed, which is what we wrote, minus sine of x plus y squared. Here's the minus sine of x plus y squared. And then 2xy minus cosine of x times y squared. So that's 2xy with in front of the cosine with a minus sign. And I think that's what I'm seeing here. Minus 2xy with a multiplied by a cosine with a minus sign. And that's what we're seeing. So f sub y would go the same way. F sub y would be equal to df of xy with respect to y. Nice, simple, compact notation. So when you try this partial derivative f sub y, this is the answer that you should get right here, and you should try that now. All right, so that's method number one for computing partial derivatives. There is another method, and I think one that will lend itself more to video 2, method number 2. Okay. This says that if you want to take the partial derivative of f with respect to x, that what you do is you take a derivative with respect to t, evaluated at f of x plus t, comma y. Okay, and then evaluate this at t is equal to 0. If, for example, you wanted to compute the partial derivative at your favorite value of x naught, y naught, where these are numbers that you're given. If you wanted to compute that partial derivative, you would take the derivative with respect to t, f of x naught plus t, comma y naught, and then evaluate that answer at t is equal to 0. Why this works is going to be the subject of the next video, but let's try to implement this method here. So if your function f of x and y is x squared y, let's do the same problem we had before. Okay. How about x squared y squared? And you want to take the partial derivative of f with respect to x. And your answer should come out to be a function of those two variables, f of x and y. Remember, this is shorthand, and this is more the long and probably maybe the better notation, but it's just kind of sometimes long to write. So we know that that's going to be the derivative with respect to t, the function evaluated at x plus t, comma y, evaluated at t is equal to 0. This splits into two pieces. You first need to find your function evaluated at x plus t, comma y, which means that wherever you see the x in the f equation, you need to substitute x plus t, and then square it. And then multiply by wherever you see the y, put in a y, and that's just y squared. So now we know that we need to compute the derivative with respect to t of x plus t squared times y squared. The answer here will be, you need to use the chain rule, 2 times x plus t to the first times the derivative with respect to t of the inside function, x plus t, times y squared. So what we've done here is the derivative of the first. This is a Calc 1 concept, derivative of the first times the second, okay? And then I need to add on plus the derivative of the second, the derivative with respect to t of y squared, times x plus t squared. So I did the derivative of the first times the second plus the derivative of the second times the first. And I think you can see here that the derivative of with respect to t of x plus t, x is like a constant here, t is the only variable, so the derivative here is a 1. So you get 2 times x plus t times y squared. The derivative of y squared with respect to t is 0. Excuse me. And therefore, you get x plus t. All right, I'm back. So we took that derivative, and now you need to evaluate this. Evaluate at t is equal to 0. When t is equal to 0, you get 2xy squared, which is the same thing you would have gotten from method 1. Method 1, f sub x would have been 2xy squared. So you get the same answer. If, for example, you wanted to compute the partial derivative with respect to y of this function, evaluated at, say, x naught, y naught, where x naught, let's say it's 1 and y naught is 2, you have two options there. You can just take the 2y x squared that you're going to get. That is the partial derivative of f with respect to y. And then you can just find the partial derivative of f with respect to y and then substitute in x is equal to 1 and y is equal to 2, which will give you 4. Okay? Or you could compute the derivative with respect to t of the function evaluated at 1 plus t, comma 2, and then evaluated at t is equal to 0. Just like we did up here where we're now substituting in our values of x and y. So if you had to go that route, you would do the derivative with respect to t, the function evaluated at, this is partial derivative of f with respect to y. Let me make this a little smaller. So you would put 1, and you need to put 2 plus t. That would be the partial derivative of f with respect to y. Okay, you do 1, and then the y gets the plus t. So then you'd have to compute the function evaluated. Let me write that again. 1, 2 plus t, and then take the derivative at t is equal to 0. Your function then would have been derivative of t squared. The function would have been 2 times x, which is 1, so that's where the 2 comes from. Y would be 2 plus t, and then you would square it. Then you need to evaluate that at t is equal to 0. In which case, now when you take the derivative, this is just a simple Calc 1 problem, you get 4 times 2 plus t to the first power times the derivative of 2 plus t, just gives you a 1. So you would get 8 8 plus 8t, evaluated at t is equal to 0. Okay, and therefore you get, according to this, you get 8. That's supposed to give you the same answer as your partial derivative of f with respect to y. I think I can see it right here. When I took my partial derivative of f with respect to y, I'm missing, when I took the derivative of y squared, I should have had an extra 2, so that should be a 4. 4yx squared, in which case this would be an 8. So these numbers should match. Okay, so those are the two methods for computing. The second method for computing partial derivatives, f sub x, is the derivative with respect to t of your function evaluated at x plus t comma y, and then evaluated at t is equal to 0. If you then want to find f sub x evaluated at x naught y naught, you can just take your answer for f sub x and then evaluate it at x is equal to x naught and y is equal to y naught. Or, if you wanted to find f sub x evaluated at x naught y naught, you could get the same answer by doing the derivative with respect to t, f of x naught plus t comma y naught, take the derivative and set t equal to 0, and you'll get all the same answers. Okay? If you want to take the partial derivative of f with respect to y, the derivative with respect to t, f of x comma y plus t, the plus t goes in the y entry, you get t equals 0. So it's probably a good question. So the subject of the next video is why / how / what is going on with that these answers via method 1, what is all this about the derivative with respect to t? Because this sounds like we are using curve lingo. In class, our time variable was like our parameter. So we'll have more to say in the next video about the interpretation of what all these partial derivatives, the meaning of these partial derivatives. And that would be the next video.